Hi, this lesson starts chapters 1.4 through 1.6 of Precalculus. Primarily, we're going to be looking at parent function graphs. This is the first of two lectures, okay? So today we're pretty much just focusing on the various parent function graphs and interpreting the slope of a line. The second lecture will look at transforming functions by shifting it or stretching it, okay? And then we'll also do reflections. Okay, first off, we're going to be looking at parent function graphs because many graphs can look very similar to each other and as a result share those similar characteristics, okay? In this case we have three graphs, x squared, 2x squared, and x squared plus 4. Okay, something we can say about all of these graphs is that they are even graphs. We know that they have a minimum. We can calculate where that minimum is. They'll have zeros. And so by looking at this and grouping functions together, you may be able to say what kind of graph you're going to be looking at. This is especially useful when you're analyzing data in science. Okay, because this is the list of parent function graphs we're going to be looking at. The first one is a constant graph, okay? Y equals 2 is an example of this, okay? When I graph it, it's going to be nothing more than a straight horizontal line. This is a function, it passes the vertical line test, but it's not very exciting. The next most common one that we'll see is probably going to be the linear graph. Okay, we've seen this a lot, and this graph has the form y equals x in its most basic form. We will be looking at this in more detail today and go to the more standard format that we're used to thinking about it as y equals mx plus b. In tomorrow's lecture, we'll look at the m and the b and see how that changes this function y equals x. Okay, other parent functions that we'll be taking a look at, y equals x squared and y equals x cubed, the quadratic and cubic. Okay, that's what these equations look like. A couple of other odd ones that we'll see, we'll have a square root graph. It looks like this. Okay, and the inverse graph looks like this. Okay, the inverse graph is an odd graph. The function is odd, and anytime we get data and when we graph that data, it falls under one of these parent functions, then we can make approximations or estimations as to what's going on or what kind of relationship exists between these two sets of data. Okay, last one's graphs that we'll be looking at parent function wise. We have an absolute value graph, okay, it looks like this, and the greatest integer function graph, which is kind of different, but we'll cover at some point. Okay, so linear functions. Okay, the most basic linear function that we have, y equals x, is an odd function. Okay, it's x to the 1. Okay, and the domain and range of this function is clearly just minus infinity to plus infinity. Okay. The more general form we probably know it in is the y equals mx plus b, where m is the slope of the line and b is the y-intercept. Okay, the slope of the line m can tell us a lot about a function, so we're going to look at m in a little more detail. Okay, like I said, m is the slope, and I can calculate the slope of a line as long as I have any 2 points on that line. Okay, and so if I have 2 points of data and it looks linear, I can more or less calculate a slope by just taking y2 minus y1 divided by x2 minus x1. Okay, sometimes we describe this as delta y over delta x or rise over run. Okay, hopefully this isn't new to anybody, but it also doesn't matter what order. It doesn't matter what order your points are in, okay? Any 2 points, okay? It doesn't matter which one is point 2 and which one is point 1. If I flip this and make it y1 minus y2 divided by x1 minus x2, okay, I still end up with the same m, okay? Because both signs on the top change, okay? So let's interpret that slope, okay? Because that m tells us, we can learn a lot from that m, okay? If m happens to be positive, greater than 0, okay, it means that your line is increasing. Remember, we had increasing, decreasing intervals. So in this case, a positive slope indicates that the line is increasing, and a negative slope indicates that the line is decreasing. A 0 slope indicates that the line is flat. Okay, and that's going to be an important feature going forward, especially when we get to calculus. The last possibility for a line is that it's vertical. Okay, we won't see this very often because one, it's not a function. Okay, it fails the vertical line test because every point on that line is on the vertical line. But it has an undefined slope, okay, because you're dividing delta y over delta x, and if my delta x is 0, then it's undefined. Okay, there's a second form of the point formula that we will that could be very useful. Okay, each will actually run into 3 different forms. We already saw the slope-intercept form, which is y equals mx plus b, and this is going to be the point-slope form. This form is very useful when I have a slope and only one point. Okay, and in this case, the formula turns out to be y minus y1, the y point. The y part of the point, and m, the slope, times x minus x1. Okay, so you see that there's only one point here. Okay, it's y1 and x1 and y1. There's no x2, y2. Okay, but I also have the slope in this case, m. Okay, and this equation, y minus y1 equals m times x minus x1, can be simplified back to y equals mx plus b. Okay, let's see how this works in practice. Okay, so a problem or a situation may arise where you're trying to find the equation of a line with slope minus 4. Okay, we know the slope from some other information. Okay, but it goes through a point that's not on my original line. Okay, now it's going to go through point 1, 3. Okay, using the point slope formula, this is fairly easy because I just do y minus y1, the 3, is equal to the slope of minus 4 times x minus x1, 1. Okay, and then I can simplify this by distributing out and then moving, and I end up with the mx plus b formula. Y equals m, it's still minus 4, x plus 7 in this case. Okay, so these are the 2 formulas for the same line, minus 4x plus 7, or y minus 3 equals minus 4 times quantity x minus 1. Okay, and then this is the third form. Okay, this form of the line is the general format. Okay, it's labeled ax plus by plus c equals 0. Okay, the advantage of this formula is it's very easy to draw a graph given this formula. Okay, because I can find the x and the y intercepts very easily by just setting the other variable to 0. So if I wanted to find the y-intercept, I set x to 0 and solve for y. All I'm left with is by plus c equals 0. Very easy to solve for the intercept. Same for the x-intercept. Once I have the 2 points on my graph, and I can find those 2 points very easily because they're on the axes, I just can put a ruler across those 2 lines and draw a straight line across them. Okay. And again, I can solve this format ax plus by plus c equals 0 to get the original format that we are used to, which is y equals mx plus b. Again, let's take another look at this slope. Okay, that m. Remember I said there could be situations where you know the slope, but it goes through a different point. Okay, and the reason for that may be because I have a parallel line. Okay, because any 2 lines that have the same m, have the same slope, okay, are going to be parallel. So in this case I have graphed in blue y equals 2x plus 3. The slope of that line is 2. The red line is y is equal to 2x minus 1. And you can see in the graph that these are 2 parallel lines, meaning they never meet. Okay, they'll always maintain the same distance from each other. Okay, so here's an equation. Okay, here's a sample. Okay, write an equation of the line passing through minus 2, 5, and parallel to the line whose equation is y equals 3x plus 1. So again, I'm only given one point, the minus 2, 5. But because it's parallel, I know what its slope is going to be. It's the same slope as the equation slope, or 3. So I would go with the point slope formula, where y minus the y1 of 5 is equal to 3 times x minus x1, x1 being minus 2 in this case. Simplifying that, I end up with y minus 5 equals 3x plus 2. I can pretty much leave it in that format unless I'm requested to do the the slope-intercept format. Okay, I should say slope-intercept, not point-intercept. But in this case, setting it to y equals mx plus b, I can solve the equation, and I end up with y is equal to 3x plus 11. Okay, so that's how I can use the parallel interpretation. Okay, parallel lines have the same slope. Anytime we have parallel, we can also talk about perpendicular. Okay, so if two lines have slopes m1 and m2, then I can say the two lines are perpendicular if they are negative reciprocals of each other. In other words, m1 is equal to minus 1 over m2. Okay, or in other words, if I multiply the two slopes, m1 and m2, and I get minus 1, then the two lines are perpendicular. Okay, last way to think about it, okay, if m1 is some fraction a over b, then m2 would be the negative fraction b over a. Okay, so again, let's take a look at this. Okay, write the equation of the line passing through minus 2, minus 6, and perpendicular to the line whose equation is x plus 3y minus 12. Again, I only have the one point, so I'm going to go with the point slope formula. Okay, but I need to find the slope of my first equation. Well, I can do that by setting it to y equals mx plus b and solving. And I find the slope of my first equation is minus 1/3. Going to the point slope formula, I find y minus the minus 6 is equal to 3 times x. Well, since my slope of the original line is minus 1 over 3, then the slope of my perpendicular line must be positive 3 over 1, or just positive 3. Okay, so we see here, okay, this minus 1/3. Well, m2 then must be minus 3 over 1, okay, or basically just 3. And that's why I have this slope of 3 here. Solving that, I basically find that y is equal to 3x, okay, and that's the slope, that's the formula of the line that goes perpendicular to the first one, going through the point minus 2, minus 6, okay? Last thing I want to talk about is that difference quotient that we looked at in the previous presentation. Okay, remember the difference quotient is that f of x plus h minus f of x over h. Okay, in the case of a line, if my line is mx plus b, and I do that whole difference quotient and simplify it, I find that my difference quotient in that case is nothing more than my m, or the rate of change for my line, which makes sense because the slope tells me how much y, or how much f of x changes based on how much x changes. Okay, which if you think about it is nothing more than the slope of my line. Okay, so we can run into situations where maybe my graph isn't a line, but I'm still trying to find what the average rate of change between any 2 points is. Okay, and to find that, I can just take those 2 points and draw a straight line across them. That line is called the secant line. Okay, and the slope of that line is effectively what I am calculating when I do that difference quotient. Okay, and so I'm basically finding with that difference quotient the average rate of change for that function. Okay, and if my h is very far apart, or the difference between the 2 points is very far, then most likely that average is not very accurate in general. Okay, because I don't really know what's going on between them. But as I move those 2 points closer and closer together, then it gets to be more accurate, and I get to actually talk about the slope of my function, okay, at those specific points. And next you will actually talk about what that really means as that delta x gets really, really small. Okay? Thank you.